Hey, today we're going to use what we've learned about differential equations to construct some models of the growth of the world population. And so we're going to consider some function that I'll call p, a function of t in time. P is the population of the Earth in billions at some particular time t. Getting right down to the calculus of the matter, that makes dp dt, the derivative of p, the rate of change of the population, or how fast people are being added to the population. And it's easy to look up some numbers. In the year 2000, the world had about 6.1 billion people, and in the year 2020, about 7.8 billion people. And doing a little subtraction, we see that that's an increase of 1.7 billion people over a span of 20 years. Do a little bit more research, and you'll find that in the year 1800, there were about 978 million people in the world. And so here's the question. Would you expect there to be 1.7 billion people more than that in the year 1820? And I hope your answer was no. An increase of 1.7 billion people when you're starting with less than a billion people would be quite shocking compared to an increase of 1.7 billion people when you're starting with just over 6 billion people. And so the idea here that I'm trying to get across is that the rate of change of the population has something to do with the size of the population. It makes sense for a larger population to have a larger rate of growth. And one reasonable model is that the rate of growth of the population is proportional to the size of the population. Or writing that mathematically, dp dt, the rate of change of the population, is some constant times the population. And the beauty of this equation is, first of all, that it's a differential equation, and second of all, that it's a separable differential equation, and we know how to solve separable differential equations. So take a couple of minutes, solve this differential equation, pause the video, and when you're ready, start it back up. Let's make ourselves a little room. First, we separate the variables. We get the p's on the left, the t's, which there are none except for the dt, on the right. K is just a constant, so we may as well leave it where it is. And then we can integrate both sides. We get the natural log of the absolute value of p is k times t plus some other constant that we'll call c. We've done problems like this before. You raise e to both sides to get that the absolute value of p is equal to e to the kt plus c, and then you use the properties of exponents to rewrite e to the kt plus c as e to the kt times e to the c, and you recognize that e to the c is just a different constant. And that lets us drop the absolute values around the p because that constant c could either be positive or negative. Now, this is a very famous differential equation. It starts in lots of problems where the rate of growth is proportional to the amount present. It's the equation of what's called exponential growth, and you will never see the answer written in this manner. And the reason is, take a look at what happens when you plug in t equals 0. You get p of 0, or the p or population at the time 0, is the constant c times e to the k times 0. Well, k times 0 is 0, and e to the 0 is 1. And so we get that this constant c is just the population at time 0, which we usually write as p0, p sub 0, the population at time 0. And that lets us rewrite our population equation as p of t is p0 times e to the kt. And this is the general formula for what's known as exponential growth. We're doing it in terms of the human population of the planet Earth, but it also applies to the spread of infectious diseases. Compound interest is another famous example, the growth of bacterial colonies and things like that. It also applies to radioactive decay in a very precise and useful way. But continuing with the example that we've been trying to pursue, the world population, we still don't have an equation here that we can actually use to say, well, what will the population be in a certain year? And part of the problem is we haven't really said what t is yet. And so I will. Let's let t be the number of years since the year 2000. And part of the beauty of that is that's one of our data points. We know what the population was in the year 2000, and so that tells us what P of 0 is equal to. P of 0, which is P0, is 6.1 billion. There were 6.1 billion people in the year 2000. And so our equation becomes P of t equals 6.1 e to the kt. We still can't plug in a number and come up with a value because we haven't figured out what this number k is, this constant k is yet. And yet we know one more data point, and that's enough to compute k. We know that in the year 2020, there are 7.8 billion people, and so P of 20 is 6.1 times e to the k times 20, and it's also 7.8. And we can solve this equation for k. And you do the usual algebra, go slowly through it if you need to, and you come up with k is equal to 1/20th the natural log of 7.8 divided by 6.1. Just some number. And if you plug that into a calculator, you'll find that k is approximately equal to 0.0123. Really, it keeps on going forever and never repeats, but we'll use this as a close enough approximation. And we now finally have an equation that should tell us the world population in any given year based on our assumption that the rate of growth was proportional to the size of the population. Let's make some more room and see if we can make some predictions. Our equation tells us that in the year 2050, we can expect there to be about 11.3 billion people, and that in the year 2100, there should be about 20.9 billion people, and that in the year 2500, there should be about 2,859 billion people, or 2.8 or 2.9 trillion people. And that seems rather ridiculous, and you say to yourself, that can't possibly happen. There must be something drastically wrong with our model. And if you look at a graph of our model starting in the year 10,000 BC and going up to approximately the year 2020, then it certainly does look ridiculous. On the other hand, if you look at a graph of the actual world population from 10,000 BC to at least the year 2000, it looks remarkably very similar to what we just came up with. Here they are next to each other, and then aside from some, jaggedy stuff in the middle, it turns out that our model may be not so ridiculous after all. But can the world really hold 2.9 trillion people in the year 2500? It's the same question as, can the exponential growth of our population really continue? And the answer is obviously not, because the numbers just keep getting bigger and bigger and bigger. And at some point, we're standing on top of each other's shoulders and standing on top of the shoulders of people on each other's shoulders, etc., etc. And so at some point, you have to take into account what's known as the carrying capacity of the planet. How many people can it really hold? And this is a very complicated question, but clearly influences the population in some way. And modern estimates include 12 billion as a sort of conservative middle-of-the-road estimate, 1 to 2 billion living in prosperity, kind of like that one. Or there's this one, 33 billion people fed on minimum rations and using all suitable land for high-intensity food production. So that's sort of the two ends of the spectrum. Somewhere between 1 billion and 33 billion are what modern estimates of the carrying capacity of the planet are. And so our model for exponential growth, even though it looks like it might have tracked the historical population reasonably well, has to break down at some point. For some reason, carrying capacity is usually denoted by the letter K. And there's a population model that takes the carrying capacity into account, known as logistic growth. And it's given by this differential equation here. The rate of growth of the population is some constant times the population times this factor of 1 minus the population divided by the carrying capacity. Let's look at what's interesting about this. if the population is very, very small compared to the carrying capacity, so that fraction p over k is a very small number, think 0 in your mind, or something very close to 0, then this looks very close to the exponential growth equation. In other words, if that p over k is tending to 0, this is just the rate of growth of the population is proportional to the population. C times P times something that is more or less 1. On the other hand, if the population is very close to the carrying capacity, so that fraction P over K is some number very close to 1, then that factor 1 minus P over K gets very close to 0, and the population growth gets very close to 0, because it's C times P times some number that's nearly 0. And so as we get close to the carrying capacity, the growth of the population starts to go to 0, which seems reasonable. And the beauty here is that this too is a separable differential equation. It's a somewhat more complicated differential equation, and I'm going to walk you through it. We do a little bit of algebra to separate the variables, and then I don't like having the fraction in the denominator on the left, so I'm going to multiply on the left by k over k, and after we distribute in the denominator, we get this expression here. And now we're ready to integrate both sides, and we could continue to go on and do this in general, but just to make things a little simpler on ourselves, let's consider the special case where the carrying capacity is 12 billion people. That gives us this pair of integrals here. The one on the right is easy. How would you do the one on the left? Think about that for a second. And hopefully you've come up with the idea that you need to do it by partial fractions. You write 12 over p times 12 minus p as a over p plus b over 12 minus p. Multiply both sides by p times 12 minus p. And that gives us this expression right here. And if you plug in the values p equals 12 and p equals 0, you immediately get that b is 1 and a is 1. Which lets us rewrite our integral as so, and now we can just integrate. You have to be a little bit careful when you integrate 1 over 12 minus p. Do it carefully by substitution, and you'll see that this negative sign gets introduced. And on the right, the integral of c dt is c times t plus a constant. We usually use c for the constant, but we've already used c, so I'll use d. And I'm going to make a little room. I can use the properties of logarithms to combine those two logarithms into the log of p divided by 12 minus p. And raising e to both sides gives us this expression here. And then it's the usual game. We write e to the ct plus d as e to the ct times e to the d. E to the d is just a different constant. I'll call it d. And that also lets us get rid of the absolute values, since d can be either positive or negative. And now there's some algebra to do. I'd like to solve for p. I'll start by multiplying both sides by 12 minus p, which gives us this expression here after we distribute. And then I'll get everything with a p onto the left side of the equal sign, which lets me factor out a p on the left, and then you can divide by what you've left with to get that p is 12 times de to the ct all over 1 plus de to the ct. Which is almost good enough, except that I'm going to want to do some computations with this, and I can make it simpler so that I can make the computation simpler by doing a little bit more algebra. In particular, I don't really need a de to the ct in both the numerator and the denominator. If I divide the numerator and denominator by de to the ct, same thing as multiplying the numerator and the denominator by 1 over d e to the negative ct, I get that p is equal to 12 over 1 plus d e to the negative ct, where here it's a different d. This is 1 over the previous d, but it's just a constant. I talked about doing some computations with this, but unfortunately I have these two numbers that I don't know, d and c, and so first I have to figure them out. First thing I could do is, I know the population at time 0, so I may as well plug in t equals 0. At t equals 0, the population should be 6.1 billion. And this simplifies to 12 over 1 plus d is equal to 6.1. And you plug that into a calculator and you get that D is approximately equal to 0.967. Moving over to the left, just because there's some room there, I know one other point. At the time t equals 20, I know that the population is 7.8 billion people. Now I also know D, so I can use this information to compute C. And you go through a bunch of horrible arithmetic and algebra, and you find that C is approximately equal to 0.029. And so making some room again, we get our final formula that according to our logistic growth equation, the population is 12 over 1 plus 0.967 e to the negative 0.029t. And just for fun, you plug that into a calculator to determine an estimate for the population in the year 2050, and the logistic growth equation gives us about 9.8 billion people. And if you look at the population in 2100, you get 11.4 billion people. I think we had 20 billion people or something like that with the exponential growth equation. And if you go far enough out, if you look at what happens in the year 2500, we are very, very nearly a hair's breadth away from the carrying capacity of 12 billion, as opposed to the 2-point-something trillion that we found with the exponential growth model. So let's take a look at a graph of our logistic growth function, and you say to yourself, looks a whole lot like the exponential growth function. And the reason is we really just didn't go far enough out on the x-axis to see where things change, where that carrying capacity starts to influence things. And now you look at the graph and you say, wow, that's the most horrible graph I ever saw. And the reason is because we're trying to go from 10,000 BC to somewhere past the year 2020. And, not much interesting happens in those early years when we're way below the carrying capacity. But if you zero in and you just look at the years where we start to approach the carrying capacity, then that's where the beauty of the logistic curve really comes in. Somewhere around 1800, when there was less than 1 billion people, we were experiencing exponential growth, but as we got closer and closer to the carrying capacity, you can see what the equation of the logistic curve did. It tapered things off so that we were not going to go above the theoretical maximum carrying capacity of the planet. So you get this beautiful curve right here. Okay, that was an application or a couple of applications of differential equations to the population growth of the planet. I hope you found it interesting. There is a new homework on differential equations. You didn't even need any of this for most of it. You were all set for it anyway, except that the very last question considers yet another possible population model. And so it's interesting and slightly challenging. So have some fun with all of that, and I look forward to seeing you in class.